Welcome to my talk about solid principles. I've been working on solid principles for a couple of years now. I'll talk about myself a bit. Everybody seems to do that. My name is Jasper Stafleu. I'm working at developers.nl, who sent me to various different jobs. I'm currently working at mijnoverheid.nl. For the Dutch people here, probably quite well known. In the past, I've worked at sites like Beslist, SBS, on the Kijk platform, and lots of other very interesting jobs. For the people that are watching this via YouTube, my picture is up there, so you also know what I look like, unlike everybody here in the audience that can actually see me. Solid principles. I was at a meeting, not too dissimilar to this one, a couple of years ago, where a speaker talked about the solid principles. He took 45 minutes to go through all 5 of them, explained them okay-ish, but 45 minutes is by far not enough to actually talk you through it in a proper way. So I've been, since then, I've been looking into solid myself a bit, and I've been, I've been trying to be more aware in my development process, particularly in my code review process, on whether these were broken or not. And there were a couple of things that I found out that prevented bugs from showing up in the future. Not even at that moment itself, but later on. Solid, well, you see the 5 principles that are over here. It's 5 simple principles that if you adhere to them, you will make better code. You will not only make better code, because it doesn't necessarily apply to code itself. It applies to everything that is component-based. If you're building a server park, some of these principles will be important as well to use. If you're building a protocol, for example, you're deciding to write a queuing protocol, AIM-Q, you're trying to implement that queue, it's also important to use the solid principles to actually not make mistakes that other people will be finding bugs on. I will not treat all 5 of them. Like I said, 45 minutes is by far not enough to do that well enough. I will be focusing on Liskov and dependency inversion. I will shortly discuss the other 3, just as a reminder for what they are for the people that don't have them at the top of their mind. I have decided to focus on these 2 because they are A, the least well understood, B, most oftenly done wrong in PHP, and C, whenever someone gives a talk for 45 minutes about these principles, these 2 are the 2 that don't show up for very long. I'll start with the 3 principles that I'm not going to tell you some more about. I'm just shortly discussing them. The single responsibility is probably the most important principle out there. It's also the one most people do right, which makes them less interesting in a lot of ways. Single responsibility basically says, if you have a class, if you have an object, if you have a component that does something, make sure it is the only one that does that. That goes 2 ways. It goes both in the direction that anything that has that responsibility must be that object, and there must not be more objects that have that responsibility. This means if you have a bug and it looks like something to do with that responsibility, you know where to look. You don't have to go through all of your code because there's separate places where this can go wrong. In PHP, this is done quite okay, well, most of the time. Responsibilities are sometimes a little bit mixed. Usually it's fine, and it's easily spotted as well. It's quite low-hanging fruit to fix this if you're doing it wrong. Interface segregation is, in my opinion, the least important of the 5 principles. In a way, I even think that it's only there because solid sounded better than salt. Interface segregation is basically a single responsibility principle applied to interfaces. Because the principle says if you have an interface, and that interface contains more methods than you actually need, then you should split up the interface into the methods you do need and only require those. This means that when you actually start implementing something that uses that interface, you do not have to implement the entire class, only the subset of methods you actually are going to need. So it makes it easier to switch out components, which is a good thing, because it makes your code more reusable and easier to swap in and out. In other words, string responsibility for principles, make sure it has one responsibility, make sure it doesn't have any other responsibilities, and make sure it's the only one that has that responsibility. So I'm not entirely sold on this part. In the PHP, this is rarely done right. That's a bit of the disadvantage to it. Of course, it's also less, in my opinion, less bad to do it wrong. It's also quite easy to actually implement yourself because you can inherit multiple interfaces in, well, almost any language, but in PHP as well. So splitting it up is trivial. Open-closed principle, the third one I'm not going to go into more detail, is the second most important principle in my opinion. It's actually two principles, which shows how important it is. It's a closed principle which says that any code should be closed for modification. It basically means if you have built a class, please do not change the class anymore. That's quite important because if you change that class and something else extends it or depends on how that class is working, is doing its job, it might break and you might not know where it breaks. It might even not be in your code. It means that the closed for modification is quite important in libraries. It basically says if you use library code, don't change the code in the library. Which we used to do wrong way back. Everybody used to download PHP libraries and then just modify the stuff they wanted to do and then put it in with their code. Then came Composer, and now we're all doing it right. Because running Composer update on code that's actually changed, well, it sucks. So if you're doing that, please stop doing that. The reversed side of this is the open principle. Code needs to be open for extension, not for modification, but for extension. So that if you do find a bug in a library code, you can actually extend that method and solve the bug in the extended part. It means you don't have to change the closed code, but you can actually fix the bug nonetheless. This is mainly a problem for library code. If library code somehow makes their code closed, I'm thinking of example using the final keyword, which I hate, never do that. If you do use the final keyword, you can't extend the class, you can't fix bugs unless you're actually sending the code to the library itself, which means people have to accept your merge request, have to understand your merge request, which is not always the case, etc. But in your own code, well, if you're coding, you probably don't have that restriction. You can change your own code as you want. After all, that's what we do all day. So in PHP, this, in my opinion, this goes wrong quite often. There are a lot of libraries, a lot of often used libraries that keep their code, close their code for modification. They use the final keyword. I have a very interesting opinion on private and protected variables, which I will not go into on this subject. Doctrine, for example, uses a final query object, which sucks. I can never actually unit test anything that uses it because, well, I can't mock it because it's final. So it's often done wrong, but most people here in the audience are probably not library builders. You probably built an application using libraries. So, well, you can keep your code closed if you absolutely want to. I wouldn't advise it, but you can. So, on to the actual principles that I want to handle. And I'll start with Liskov. It's the one I'll take the longest bit about. Liskov is named after Barbara Liskov. Unlike all the other letters in Solid, this one is actually named after someone that came up with part of this principle, instead of just being the principle. Once again, that's probably because solid sounded better than SOSIT, which would be the alternative, as the better name would be strong behavioral subtyping. Let's start with a definition. I'll let you read it. I'm not going to read it aloud to you. Well, let's have a show of hands. Who here understands what this says? Well, actually 2 or 3 people. That's a lot better than I expected. This sucks, let's face it. If you're going to read up on the Liskov principle in this case and you get to see this, you're going to say, well, what the hell am I going to do in my daily programming practice to actually apply this? I personally like math speech, but it's not the best way of communicating this. Let me translate it a bit for you. It states that any class should be allowed to be replaced with an instance of a subtype of that class without altering the correctness of the program. So if I'm actually, let's see an example of that. If I have this code, I have origami. Origami makes airplanes out of paper. Everybody knows that. We have paper. We have papyrus, which is a type of paper, so we extend paper. And then we can call new origami make airplane new papyrus. Okay, this is fine. It's, I mean, PHP accepts this from us. We can do this. So looks pretty trivial, right? We can actually extend paper. We can extend a class, and its subtype will be accepted by the code. Yes, it might just be that trivial. Let's see an example where it's not. This is that example. Because what we're doing now is saying, well, origami uses a default method to actually build an airplane out of paper. And folding it, well, in the case of paper, it divides the area by 2 or does whatever. Doesn't really matter. But papyrus is a weak type of paper, which cannot be folded. It will break. If anybody here knows more about paper than I do, which is quite likely, maybe papyrus doesn't fold. Let's keep it in the example nonetheless. So what happens here, we have an expectation from origami that we will use paper. And paper says, I can fold. So the correctness of the program actually depends on paper being foldable. Papyrus is not foldable. It throws exceptions. In fact, while papyrus in the previous example was a perfectly fine extension of paper, it is not over here because it does not hold. It cannot be replaced in the program without altering the correctness of the program. There are several ways in which we could fix this. We could have paper, for example, have an annotation saying at throws cannot fold exception. At that moment, we are actually stating that fold could throw a cannot fold exception, in which case papyrus is suddenly perfectly fine. We nowadays have scalar type hints in PHP 7 to actually show these kinds of, to actually make the input and output variables more fixed in what version they are. I would like to see in the future something that actually states what the method can throw in the language itself. Currently, we cannot do it much more. We cannot do it stronger than just putting it in the annotations. You could also say throws any exception. It's also fine. After all, I'm going to assume that cannot fold exception extends exception. So we're expecting that it could throw an exception, also fine. This is one of the 4 types that have been identified in which you can break the Liskov substitution principle, in which you can make an extension of a class that does not actually fit the class, which breaks its expectations. I'll take up the other 3 as well while I'm doing it, which starts with strengthening preconditions. Preconditions are things that must apply to a class, must apply to an object, to a component, before you can use it in your program. And Liskov says that those preconditions are not allowed to be strengthened. In this case, we're showing we have an iEngine, and we have a jet engine that implements that interface. We have a jumbo jet that requires that interface for its add engine method. Jumbo jet is not much without an engine, won't fly very far. So obviously it needs that method. Then origami will use that method. We add an engine, new jet engine. Well, okay, fine, no problem here. Let's implement the propeller, which we need for a triplane. Triplanes extend jumbo jets, but, well, I don't know if anybody has ever seen a triplane with a jet engine. I haven't. So we're going to say, well, it doesn't need any engine, it needs a propeller. Okay, you might say that's fine. The only thing we're saying is we're being stronger in our requirements. We're being more strict than the parent clause. But obviously, if we're going to make an airplane out of paper, and we're going to say that that the airplane is not being created into a jumbo jet, but into a specific type of jumbo jet, namely a triplane, and we're going to add a new jet engine to it, we're going to get an error. So once again, we have broken the correctness of our code by extending and breaking our promises. Thankfully, this example will throw a warning in PHP. PHP just forces you to have the method names of the method handles of extended classes to be exactly the same. So this, while there are probably languages that will allow this, PHP throws a warning, but does continue trying to do it. So you will still get a fatal error once you're actually doing this. What you're seeing is that the error will be shown here, but the actual bug is over here. So you have a problem here that the location of the bug and the code that causes it is not the same. This is something you'll often see in Liskov, that bugs are not where they are supposed to be. They are in a particular piece of code, but they are triggered by something completely different. Let's see a stronger example of strengthening preconditions, which has to do with the engine, which has a get max speed. Somebody already told me that engines do not have speed, they have power. I tried to change the examples to fit that model, but they became very convoluted. So you're just going to have to stick with me that engines have speed. We implement the space shuttle. Space shuttle is also a type of jumbo jet for some reason. We're going to add an engine to it, which is nicely an I engine. We saw in the last slide that this is allowed. But we are going to say this engine has an additional precondition, an additional strengthening of our preconditions, which is we need a maximum speed of at least 11,200 meters per second, which is more or less escape velocity, which we need to actually send our space shuttle out of the atmosphere. So we're once again making a mistake. We are once again strengthening our preconditions. We are actually saying, well, in order for this engine to be accepted, it needs to be fast enough. It didn't need to be fast enough for jumbo jets. They just took any engine you gave them. So once again, if you're going to use origami to build a space shuttle in this way, well, we might have bugs. We might not even have bugs always, because some engines will be fast enough and will be allowed. But somewhere along the line, we are going to get a bug that the engine isn't fast enough. Which is bad, because somewhere along the line might be 3 years from now, when everybody that actually worked on this code and understood it has long gone. And well, then if you are the person that has to fix it, then, well, it sucks. I think we've all been there somewhere along the line. A different type of Liskov breakage is the weakening of post conditions. It is very similar to strengthening preconditions. Yes. Weakening post conditions is basically the reverse. Instead of having our input variables, everything we put into the method, being stronger than we needed, we are now actually weakening what is coming out of it. So in this case, we have a slingshot propelled shuttle, which is a type of space shuttle, but it doesn't need an engine that is quite as fast, because we will give it an extra push with a slingshot. We add an engine, and this engine, well, this engine does not need to be faster than 1200, faster than escape velocity. And well, just to test that, just to show that, we set it that self-propelled is false, which doesn't truly matter. What we're doing now is building a space shuttle, which we had the post conditions of that we could actually launch it out of the atmosphere. And we've actually built a space shuttle that can't be pushed out of the atmosphere by its engine. Or if we give it specific types of engine, it will not be pushed out. So what we're doing now is we have a slingshot propelled shuttle. We're building that from paper. We give it an engine. Everything goes fine. We are not getting any errors. We shoot it into space and it doesn't happen. Well, that's a couple of $1 billion to thrown away again. Especially if we try to launch it, and we launch it like this. We have a launcher. It has a function escape world. And we're just going to say while the speed of the shuttle is not yet escape velocity, we're just going to go faster. Of course, if the engine suddenly says, well, I can't go faster anymore, you can go faster with whatever you want. You're not going to get there. Nasty bit here, this launcher could have been introduced in the code 3, 5, 10 years later and works fine on every space shuttle except that one person somewhere thought of a slingshot propelled shuttle. Once again, the error is not in the launcher. It might have been added as code later on, but it does not contain the actual bug. The actual bug is in the slingshot propelled shuttle, which is basically too slow. And we promised that it would be fast enough. The final type of Liskov breakage is the history constraint. The history constraint is a bit harder to understand. And it basically states that you are not allowed to change behavior parts of the class that could not be changed in its parent class. As an example, we have here a solar-powered engine, which extends a jet engine. This solar-powered engine is obviously powered by solar rays, and how fast it can go is dependent on how intense the solar rays are at the moment. So if there are clouds, well, we're going to go slower. So suddenly, in our previous examples of the jet engine, or of the space shuttle, the jet engine, we actually knew what the max speed was at all times. It was a constant. We could check the engine once and let it tell us, I am fast enough. We can't do that here. After all, the max speed changes constantly. So while in earlier implementations we were actually saying, well, I am going to promise you that this plane is going to be fast enough, that this engine is fast enough to be put on this plane, we are suddenly saying, well, we are only promising that this engine is fast enough at the moment it is being installed. Not everybody is going to be happy about that. In a way, this is quite insidious. It breaks not even the code, it breaks a promise the interface is making. It says, I have a max speed. That max speed is kind of implied that it is a constant, and it suddenly isn't. You could prevent this using a private keyword on the max speed. I just told you that I'm not a fan of private due to the open-close principle. And even then, if you try to solve it that way, it's not going to work well, because you can still work around the private keyword. A simple solution for this is using immutable objects. We are not quite used to doing that in PHP. As far as I know, there's only the immutable datetime object, and well, I never needed it, really needed it. But immutable objects are basically, you construct them once and it never changes after that. If you're just going to say, I'm going to use immutable objects everywhere, you are never going to break the history constraint, because you're not going to have these kinds of constructs. Like I said in the beginning, not everything is code. We can break Liskov outside of coding. A good example, which I ran into at mijn overheid a couple of months ago, is that AIM-Q, the message queue protocol, in its specification it says, well, if you have a single queue, then consuming jobs from that queue is atomic. In other words, if I have 10 workers and they all listen to that one queue, only one of those workers is going to get any job on it. Which makes sense. You want this atomicity in your queuing system. And then we get RabbitMQ. And RabbitMQ, I don't know why. It is an implementation of AMQ for those that do not know about it. And for some reason, they decided not to implement this atomicity. So we actually ran into a situation where people were saying, hey, I'm getting, well, thankfully it wasn't a test environment, but they were saying, hey, I'm getting a certain mail 2 or 3 times instead of just once. It was because we were queuing, please send a mail. It was picked up by 3 workers within 10 or 20 microseconds, but it was picked up 3 times, so people got 3 mails, which sucks. And we look at the protocol. The protocol says this can't happen. It's never going to happen. And then when you go to a very obscure location in RabbitMQ, I've added a link, which you can later on look at in the slides, which states that they do not do this. You have suddenly an implementation that breaks that promise. This is also an example of breaking Liskov. We make a promise, we do not keep it, resulting in weird bugs. So, Liskov, in summary, please don't break it. You are going to get bitten by lots of bugs later on. You need to make sure that an extension at least acts or has the same kind of behavior as its parent implementation. It's quite hard to find these bugs through testing. Like I said, almost every example I just gave, you can write unit tests around and it will keep going fine. And the launcher that I just introduced, you can write a unit test about it, it will work fine. But it is the interaction between those two where the bug lies. So it is going to be hard to find these bugs using unit testing. How do you solve it? Well, first of all, please just don't do it. It is by far the easiest way of solving it. Just start by looking at your implementation. Am I breaking any expectations that I have made in my parent implementation that my child does not have? Another way of solving it in a more practical manner is don't use the extend keyword too much. Don't overuse it. Only use it if you are absolutely certain that the methods you are overriding, you can add methods what you want, but the methods that you are overriding or implementing do not change behavior of the superclass. A third way that might be a good solution is using traits, as traits contain reusable code that is not in any way really object-oriented. I think that's a problem with traits. You cannot type hint traits. You cannot check whether a certain class has a trait. Well, you can using reflection, I believe, but you shouldn't. So it might be a solution, but it is a bit of a, it's a bit out there. It's not necessarily the right solution. Okay, let's go on to the last part, dependency inversion. Dependency inversion states that abstractions should not depend on details, but details should depend on abstractions. Well, everybody in the audience probably thinks, hey, abstractions, I know that one. I can make abstract classes, it probably has something to do with that. Do not fall into that pit trap. We are not talking about PHP abstractions here. We're talking about, well, a lot more abstract abstractions. I'll give you an example. Let's start with the most common type of breaking the dependency injection principle. In fact, if you're going to look on the web, this is almost the only example we will ever see. It's not the only example that we can have. This is an adaptation of basically the school book example. We're making an airplane and we're creating the paper in the make airplane method, which means that origami can now never be done on papyrus because we have tightly bound it to paper, which means we cannot replace paper in our class, which means we are less component-based, we are less object-oriented. And if you ever want to use Papyrus nonetheless, well, you're out of luck. So this means we have a piece of code that can basically not be reused because we cannot give it other parameters to make it work just a little bit different, which makes unit testing almost impossible. I mean, you're never going to be to succeed at making a mock for the paper class, which may or may not be a problem, but in the end it will always bite you somewhere along the line. It's called tight coupling. It's basically this class is bound tightly on this one. They do not, this class, this more abstract class, cannot exist without this more concrete class. Paper being the more concrete class here. It's more concrete because it is actually being used by origami, even though the paper does not need to know about origami itself. It is basically closer to real-world objects. So this example, you'll see it a lot if you're going to look at dependency injection. But it's not really the only example we can make. We can take an airplane factory, which makes airplanes from paper, apparently. It creates paper by using paper to airplane, can create a jumbo jet, it adds engines, and well, that's it. We have a private function add engine, which does something to the jumbo jet, and we have a paper to airplane method, which is abstract. What we are actually now doing, we might have an abstract class. So you might say, well, if we are extending that using origami, it's fine. I mean, this is not abstract, this is abstract. This depends on the airplane factory. So we are actually upholding our dependency inversion principle. This is why I said PHP abstract is not what dependency injection principle means with abstract, because we're still breaking it. And we are actually breaking it over here. We are saying make airplane depends on paper to airplane method. So we have a concrete non-abstract method which depends on an abstract paper to airplane method. So if you look at it like that, we are not even looking at the abstract keyword because it's not in here, but we are breaking it. This means that origami, which uses paper to airplane, might then use add engine in itself or might do all kinds of ugly things. I have actually, in reality, run into situations where there were 3 or 4 layers of abstraction, which meant that the first class called a method that was implemented in the third class, which called a method that was implemented in the second, which then called a class in the fourth, and you were going all over the place. Impossible to debug those kind of things, especially because this might not be the only extension. If this piece of code contains a bug, if this piece of code contains a particular, well, not a bug, but introduces an expectation on how it works in the whole, it is harder to actually extend the airplane factory again, because the original airplane factory might depend in its details on the result of this abstraction. We might make an airplane that promises a certain amount of speed, or it might promise that it accepts jumbo jets. This is a bit weird. It might not even return a jumbo jet in principle. This will create bugs along the line later on if you're actually implementing another class that extends the airplane factory. And once again, we are seeing the same problem arising, being that we extend the airplane factory in a later moment. We are not introducing a bug in that piece of code because the actual bug in the code was in the airplane factory itself. Once again, there are examples outside of code. In my opinion, waterfall is breaking dependency inversion principle. I mean, everything needs to be done nicely in its place, and you cannot never go back, you can never overlap. In a way, every bit of the process is tightly bound on the end of the previous process. A different example would be RAM memory in most laptops, for example. If you need more RAM memory in your laptop, most laptops won't allow you to actually plug it out and plug more in. So it is tightly bound in it, and you are suddenly making additional dependency on your laptop which says, well, this is the maximum amount of memory I am ever going to have, even though normally you would be able to extend it. So, a small summary for it. Doing dependency inversion principle right makes your code more reusable, very simply put. If I do not use the new keyword on paper, I can actually change the paper for a different implementation of paper. In fact, depending on paper itself in your method handle is already tightly binding it to a specific type of paper. It is even better to replace the paper with an interface of paper. But this is something that you will seldom see because, well, paper is probably just a plain old PHP object, just a couple of setters and getters. And I have seldom seen people make interfaces for classes that only have setters and getters. So while it would be nicer to actually implement an interface for it, create an interface, then implement it and make sure the paper extends it, it's not always done and it doesn't always need to be done. So using interface is one way to solve it. A different is avoiding abstract classes. Once again, traits might be the hero, I'm not quite sure yet. A different way is just not using the extend keyword unless you know what you're doing. Extends, please implement interfaces, don't extend interfaces. Everybody probably heard this before. I believe we had a talk on it last year here. So that would be the solution for the dependency inversion principle. So, does anybody have questions?
Yes.
Go ahead.
At some point in the presentation about the dependency inversion, one thing was a little bit confusing. At some point we extended the factory.
Yeah.
Usually, what I know about the factory, usually you want the factory to make the object, which then usually gets extended and uses interface. I
agree. So the question is,
when would you extend the factory?
Yeah. So the question is, why would you extend the factory? Because the factory pattern itself is not intended to actually be extended, right?
Yeah.
Okay. You are absolutely correct. Factory patterns are not necessarily extended. For the sake of this example, I stated, well, I have an abstract kind of factory. It's an airplane factory. Maybe it's just an abstract class factory, which is a kind of repository for reusable code that a lot of other factories are going to use. It does not fit the pattern. You're absolutely right, but it makes for a good example.
Right, that's right.
Yeah. Anybody else? No? I have some further reading for you if you actually want to know more about it. These are the ones that I referenced in the presentation. But this is not all there is. There's a lot of information on the solid principles out there. And that's it. Thanks for listening.